Hello and welcome to today's lesson where we're going to be going through power and energy transfers. We're going to be going through these 3 pages of the booklet, and there's plenty of opportunities for you to have a go at answering some questions because we're going to meet quite a few equations today. So first off, we're going to be starting with this page looking at power. So what is power? Well, power is a word that has a few different meanings, but in physics, when we talk about the power of a device, we're talking about the measure of the energy that it can transfer. And in terms of an electrical device, this is related to 2 things: the potential difference across it and the current through it. So we can link those 2 things together to give us our first equation, the 4 that we're going to meet, which is power equals potential difference multiplied by current. Make sure you know those units. So power is measured in watts, potential difference in volts, and current in amps. Now there are a couple of other equations for power, and this is another one that you need to know, and you can derive it from the original equation if you'd like to, but this is power equals current squared multiplied by resistance. Resistance, the only new one there, and the unit for resistance is ohms. So before we move on to energy transfers, you'll see at the bottom of the previous sheet there are some questions that you can have a go at and see if you can use those equations to work out the answers to them. Then we're going to move on to this page, which is energy transfers in everyday appliances. Now, electrical appliances like this kettle here are designed to bring about an energy transfer. What I mean by that is this kettle, the energy that comes in is in the form of electrical energy, but we want the kettle to transfer that energy into heat or thermal energy to warm the water up. So we describe that as a useful energy. There's also waste energies, for example, sound, when the water's boiling, that energy isn't something that's useful, and we call that waste energy. So what affects how much energy is transferred by an appliance? Well, there's 2 things. The amount of energy that an appliance transfers depends on how long it's been switched on for. Obviously, the longer that it's switched on for, the more energy it transfers. And secondly, the power of the appliance. And again, the higher the power rating, the more energy that it's going to transfer in a certain amount of time. We're now going to meet 2 more equations, which is these 2 here. So energy transferred equals charge flow multiplied by potential difference. Energy transfer, obviously being a measure of energy, is measured in joules. Charge flow, that C stands for coulombs, and we met that previously. And potential difference again in voltage. And the other energy transferred equation that you need to know is that energy transferred equals power multiplied by time. Check that time is in seconds, that's standard unit that you're looking for, power in watts, and energy transferred in joules again. Now we come over to the 3rd page where you've got some examples of some questions that you could have a go at and try out. What I'd recommend is having a go at them now, hit the pause button, and when you think you're done, press play again and check your answers. So hoping that you paused, so let's go through our answers. So the first one was the useful output energy from each of the following appliances. So we're looking for the useful output energy. So for a fan, it's kinetic energy as the blades of the fan spin. For a table lamp, obviously it's light energy. And for a heater, well, the clue's in the name, thermal or heat energy. Question 2, calculate the power ratings of each of the following devices. So the first one up is the hairdryer, which converts 40,000 joules of electrical energy to heat energy and kinetic energy every minute. So firstly, looking for your parts of your equation. So we've got time there, but noticing that time isn't in seconds in the question, 1 minute. So we need to convert it, which gives us 60 seconds. We're then going to put it into our rearranged equation, which is power equals energy transferred divided by time. So the energy transferred is 40,000 joules divided by the time, 60 seconds, gives us a rounded rating of 667 watts. Next one, a microwave which uses 1.5 times 10 to the 6 joules of energy to defrost a chicken in half an hour. So in this one, again, our time isn't in our standard units, and we've also got a standard form for our joules, which is something that they commonly use in these physics exams. So let's firstly convert our minutes into seconds. So 30 minutes, multiplying that by 60 gives us 1,800 seconds. Power equals energy transferred divided by time, same equation as the previous one. We're going to substitute our numbers in. So power equals 1.5 times 10 to the 6 divided by 1800. If you're careful, you can keep it in standard form while you're putting it into your calculator, and that gives us a power rating of 833 watts. Next question, the television has a power rating of 160 watts, a light bulb has a power rating of 40 watts, and a dishwasher has a power rating of 1150 watts. Calculate the total energy transferred by these three appliances if they're used for a period of 4 hours over the course of a day. So again, we need to convert this time from hours to seconds. So I've done it in 2 stages. So 4 hours multiplied by 60 gives me 240 minutes. And then multiplying it by 60 again gives me 14,400 seconds. Again, you could work out each of them individually and sum them up, but it's quicker to put them together. So the total power, the 160 watts of the television, the 40 watts of the light bulb, and the 1150 watts of the dishwasher put together is 1350 watts. And again, I just want to put those into my equation. So power equals energy transferred divided by time. Rearrange the equation, power times time equals energy transferred. And then I get 1,350 multiplied by 14,400 gives me 19,440,000 joules. And then finally, it's quite a nice question here. It's quite a tricky one. This sticker was found on the casing of an electrical appliance. Use the information in the sticker to determine 2 things: the minimum current that the appliance will use and the maximum current that the appliance will use. So you've got to use a bit of thought here. If we look at the sticker, we can see that the potential difference ranges from 230 to 240 volts, and the power ranges from 1100 to 1200 watts. So we need to think about which of those values will give us the answers that we're looking for. So firstly, for the minimum current the appliance will use, we're going to be using the equation power equals potential difference times current. So rearrange gives us current equals power divided by potential difference. So when we're thinking about this, to make the smallest number, we want the power to be the lowest value that we can and the potential difference to be the highest number. So thinking about the lowest power will be 1100 and the highest potential difference will be 240 volts. So therefore we do 1100 divided by 240, which gives us a current of 4.58 amps rounded to 3 significant figures. When we're looking at the maximum current, we want to do the opposite. We want the largest power that we can get, the biggest number, divided by the smallest possible potential difference. So we're going to use the opposite end of the scale for this one. So we're going to use the power of 1,200 watts and the lowest potential difference of 230, and dividing those gives us a current of 5.22 amps, again to 3 significant figures. So check off, have a look, see how well you did and what you could improve on. And there we go, that's our lesson on power and energy transfer completed. Well done.